Hi guys, it's Daniel here, and today we're going to do a number theory problem. Let a and b be co-prime integers, show that the equation ax squared plus by squared equals z cubed has an infinite set of solutions x, y, z with x, y, and z, all integers, and each pair of x and y mutually co-prime. So the first thing we notice is that it doesn't matter whether x and or y are positive or negative because we square them. So they all end up being the same value anyway. So we can assume that x and y are positive. And in addition, they can be 0, but whatever. Then we also notice that x squared and y squared are non-negative, which means that z cubed is non-negative, so z is a non-negative. So we can just assume, without lost generality, that x, y, or z are in the non-negative integers. So now what? Well, when I first read the problem, the first idea I had was that maybe you could suppose that we had one solution, ax squared plus by squared equals z cubed, and then we can multiply both sides by some sort of expression, like some mystery expression equals w cubed. If we multiply these together, and then we end up with, some sort of alternative expression ai squared plus bj squared equals to zw cubed, and then that would be a new solution. So I was thinking to myself, what exactly should we put in here so that the final result is also expressible as the ai squared plus bj squared format. So the idea was maybe I could have this expression right here be the exact same as this expression. It would be nice if we could multiply those two together and then get another expression just in the same form, ax squared plus by squared. So that is exactly what I did. Ax squared plus by squared times, let's do am squared plus bn squared. But we don't want to just expand this, because if we expand this, then it's going to be really hard to try to figure out what I and j are. So here's the trick that I did. Since they're squares, and I kind of wanted them to factor into linear terms, I just went ahead and did that. So if we factored it into linear terms via the difference of squares factorization, then we get square root of ax plus I times square root of by. This is starting to look very not number theory, so bear with me here. But we have square root of ax minus I square root of by. And you can confirm that if you multiply these together by the difference of squares operation, we get, or difference of squares factorization, we get ax squared plus by squared. And then we also multiplied by square root of a m plus I square root of bn and square root of a m minus I square root of bn. And then the idea was that instead of multiplying them first the first two and then multiply the last two together and then multiply those, I multiplied the first and third terms together and then multiplied the second and fourth terms together and then multiplied those. So if you do that, we get axm minus byn plus I times the quantity, let's see, there's a square root of ab in both of them, and then the remaining is ym plus xn. And then the other term is going to be the conjugate of this term. I chose to multiply the first and third terms together first, and then the second and fourth terms together first, and then multiply those together, because the resulting expressions are going to be conjugates of each other. And if they are conjugates of each other, then we can do the difference of squares factorization backwards to hopefully get something of this form. So if you multiply by the conjugate, I'm not going to write it out, but if you do that, then by the difference of squares factorization, you get that this thing is equal to axm minus byn squared minus ym plus xn squared. So we were pretty close, but not close enough. Because instead of getting an ax squared plus by squared type of thing, we had an a squared or x squared plus aby squared sort of thing. So, or this is just should be plus. So we didn't quite get what we wanted, which makes me kind of disappointed. But the next idea that came to me was, well, this is in a sort of similar format. So what if we multiplied something of the format ax squared plus by squared by this format, this new format, m squared plus ab n squared. What if we did this? Then maybe we could get back to our ax squared plus by squared format. So I went ahead and did the exact same thing as before. First, I turned it all into the difference of squares factorization. I square root of by times the conjugate, I'm not going to write it out, times m plus I squared of ab times n multiplied by the conjugate. And then I multiply the first and third terms together again, and we get that this is equal to, let's see, square root of a x m plus or minus square root of a b y n times I. Or no, not times I. That's the real term, and the imaginary term is I times, let's see, square root of b y m plus square root of b axn. And then the other term is this term's conjugate. So now we have another difference of squares factorization, so we can expand that and see what happens. So this turns into a times xm minus byn squared plus, let's see, we get b times ym plus axn squared. And lo and behold, this is exactly the format of ax squared plus by squared. So originally I was going to try to find some sort of term here that such that when we multiply it by ax squared plus by squared, then we get another number of the format ax squared plus by squared. But here we can see something even better has happened. Because note that how many times we've multiplied a term of this form together. We did it twice to get this expression, and then once more to get back to our expression that we desire. In other words, we've multiplied something of this form 3 times together to get something of the same form. And note that this exponent here is a 3. So this gives us the idea, what if we multiplied 3 of the same things? What if we cubed ax squared plus by squared? Then what perhaps we might be able to solve this equation by, we can generate an infinite number of solutions to this equation by starting out with an infinite number of different ax squared plus by squares. So in fact, we do find out that if we cubed ax squared plus by squared, and went through this entire process and solved for the final terms here and here, then we get this miraculous identity: ax squared plus by squared is equal to a times ax cubed minus 3bxy squared plus b times 3ax squared y minus by cubed squared. So we went through this entire process, multiplied x squared plus by squared with itself 3 times, and we got another number of the format ax squared plus by squared, where the x and y are instead replaced with ax cubed minus 3bxy squared and 3ax squared y minus by cubed. what a monster. But somehow we ended up with this. And now we see that we've almost solved the problem. Because here we have something of that format is equal to a cube. And then so in this case, our cube is just going to be ax squared plus by squared cubed. And our x and y is going to be these two numbers. So now, are we done yet? No, not quite, because we still need to prove that we can find an x and y such that this x and y are mutually co-prime. So in order to prove that ax cubed minus 3bxy squared and 3ax squared y minus by cubed is co-prime, it requires a little bit of work that is not trivial, because we have to pick x and y carefully such that it's true. It's not true for all x and y. Clearly it's not true for when x and y are not co-prime, because then the resulting ax cubed minus 3bxy cubed, etc., these are also not going to be co-prime, since we can take the same factor that divides both x and y. So a condition we must have is that x and y are not co-prime. And then it turns out that as long as we choose, without loss of generality, that a is odd, because, or sorry, not a is odd, a is not divisible by 3, because we know that a and b are co-prime integers, which means that at least one of them is not going to be divisible by 3. So if we assume without loss of generality that a is not divisible by 3, and we also choose x and y such that a, b, x, and y are pairwise relatively prime, we choose x such that 3 is not divisible, or x is not divisible by 3, and finally we choose ax squared minus 3by squared such that that is odd. Then we can prove that these two terms are relatively prime. And that's a lot of conditions, but it turns out that we can choose x and y such that all those conditions are satisfied. And the proof of why these are relatively prime is left as an exercise to the reader. And I don't believe that all the conditions I've said are the only possible conditions that you can put on x and y such that these are relatively prime. So if you can find your own, perhaps simpler conditions that make these two terms relatively prime, then I'd like to hear that in the comments. So have fun with the rest of this problem, and that's it. Hi guys, it's Daniel here, and today we're going to do question number 6 of the 2008 IMO. So since it's question 6, it means it's the hardest problem of the IMO, but don't be intimidated, because in fact